All right, let's look at 5a. So our function is f of x equals minus 2x squared plus 2. I had to edit this one out if you have something different. So we want to check that this satisfies Rolle's theorem. So f of minus 2 is equal to minus 2 times minus 2 squared plus 2 equals minus 8 plus 2 is equal to minus 6. F of 2 is equal to minus 2 times 2 squared plus 2 is minus 8 plus 2 equals minus 6. Also, CTS for continuous and differentiable. More specifically, it's continuous on the closed interval and differentiable on the open interval. So because those three criteria hold, Rolle's theorem applies. So that shows that. So f of x satisfies Rolle's theorem. Rolle's theorem. Now we actually need to figure out where is the c that makes this work. So f prime of x is equal to minus 4x, and that's it. Minus 4x. So f prime of x equals 0 when dividing both sides by minus 4, you get x equals 0. And that's from minus 4x equals 0, divide both sides by minus 4. Not too bad. B, another one I had to edit slightly, although the original still worked. So sine of 2x on 0 to pi over 2. Now let's check. So first, CTS for continuous on the closed interval and differentiable, DIFF, on the open interval. So now we just need to check sine of 0 is equal to sine of 2 pi over 2. So g of x equals this. G prime of x is going to be 2 cosine 2x. Okay, g prime of x is 2 cosine 2x. I still didn't finish what I was doing though. So sine of 2 times 0 is sine of 0 equals 0. Sine of 2 times pi over 2 is sine of pi, which is also equal to 0. So g of x satisfies Rolle's theorem. Okay, so we check to make sure that works, and it does. So now g prime of x is equal to 2 cosine 2x. We want to see the c that works. Let me fix this real quick. Okay. So we have 2 cosine 2x is equal to 0. So cosine 2x is equal to 0. When is cosine of anything equal to 0? That's that thing equals pi over 2 plus 2 pi k. So x is equal to pi over 4 plus pi k. And here you can try to plug in, but the only thing you'll get is pi over 4. So c equals pi over 4 is the only solution in that interval. Finally, part C. We have x squared plus 1 over x squared. So this at first might seem scary because that 1 over x squared, that's not differentiable everywhere. And actually isn't even defined everywhere. But as long as x is bigger than 0, then we're fine. So we say h of x is continuous on what? 1, 3 to 3, differentiable on the open interval 1, 3 to 3. Oops. And let's check. This is a cool little thing. H of 3 is equal to 3 squared plus 1 over 3 squared equals 9 plus 1/9. And I could combine like terms, but this will still work. So now I plug in 1/3 when I plug in that, and I get 1 over 1/3 squared equals again 1 over 9 plus 9. So those two are equal. H of 3 equals h of 1/3. So h satisfies Rolle's theorem. So now let's just work this out. H prime of x is 2x minus 2 over x cubed. We're setting that equal to 0. So I get 2x equals 2 over x cubed. Cancel out the 2's. X to the 4th is equal to 1, which says take a square root. X squared is equal to plus or minus 1, but we don't have minus 1 as an option because it's not in the interval. And then take a square root again, use the same logic, get x equals only plus 1. So that's your final answer. And that is using Rolle's theorem.